So thank you for being here for this second presentation about another functionality in the traffic library, about the detection of holding patterns. So actually, originally I didn't plan to do this presentation, but that's a problem when you have access to the EasyChair notification when you submit an abstract and you see many people coming with holding patterns abstracts, and I say, come on, I have to. This has been ready for years, and I have to finally write the paper. So the paper is not written, but the but the slides are here.
And it's for 2025, right? It's for the next
year.
True. Thank you. So yeah, this has been some actually work. We prepared this model that is available in the traffic library it has been available for a while already. We built it maybe 2-3 years ago, I think, together with my colleague, Luis Basora, together with Junzi and Enrico. So we focus here on a specific method in the traffic library that's not a filter anymore, that's a holding pattern. This method doesn't, so usually among the methods that you have in the library, most of the method return a new flight that has new particularities. This one is slightly different. The thing is, you can have several holding patterns in a trajectory, and so it returns a different structure that you can iterate on to get segments of your flight. So that's why you also have other methods like the next method or the label methods that, well, as are detailed in the documentation. Yeah, basically, yes, I would return either like answer question: does this trajectory has a holding pattern? Like, can you show me in the trajectory, add a column with a flag to tell me this is a holding pattern, this is not? Well, you have several ways of putting things. So. About the contributions, we actually have this label data set that we already used in a previous paper. About 2 months of data of trajectories landing at 6 airports. We have, so now some model in the ONNX format. So actually 2 files, one for the scaler and one for the classifier. And an implementation in the traffic library. Since the model is like with this ONNX files, they are actually cross-platform, cross-language, cross anything. So you can if you're more comfortable in another language, you can still use the same files and implement the same method in your language of choice. So about holding patterns. What's trying to make a definition, it looks easy to define, but when you try to formalize it, it's not that easy. So it's a flight maneuver used to keep an aircraft while waiting for the instructions. So usually you see them either around London Heathrow Airport, or I don't know, like most of the holding patterns are around London, right? And but it also happened to, for example, when you have an emergency to see like the aircraft needs to run some checklist, they enter some holding pattern anywhere, and while they run their checklist. And well, the way you recognize them and the way people like to visualize them when they do some presentation is to see, you recognize them by this kind of racetrack like loop. So you have, let's say, a straight path, and then they turn, and then another straight path, and they turn, and etc. So the first question that we can ask is like, okay, it's nice to have machine learning models, but can we do things more simply with just rule-based methods? And actually, the definition is here, like, there's a straight path, a turn, a straight path, a turn. And actually, the answer was, well, you will see in the next slides a lot of corner cases where it's actually a holding pattern, but it doesn't match this definition. So we stick to the ML-based method. So basically, you have like particular patterns. With this illustration, I forgot to change the title of the slide. But you have several ways of entering a holding pattern. Like basically you can, like, these are the four ways, but like you can have so you can enter with first a line to the navade that is documented as where the holding pattern starts, but you can have this, what they call a teardrop way of entering the holding pattern. So this shape is also characteristic of the holding pattern, but not always. You have here, sometimes you are in the holding pattern, so it's a bit oblong, but sometimes they finish that with a circle because it's time to go. It's time to go out. And sometimes you also see like a bit more like they turn in one direction and then the other, but it's still, you still see this this oblong shape that characterizes the holding pattern. And we want basically to match all those situations. That's why they, in the end, like, since I am not able to set a problem properly, I'm going to use machine learning, and it will do the definition for me as well. So you see, like in all those situations, it's actually so trajectories that are on the OpenSky database, and what is highlighted is what the final method highlights as what is a holding pattern. So you see here, for example, so it's coming to London City. They're coming from this side. They have this kind of, yeah, it's a bit too long to be a holding pattern. They enter not really directly. It doesn't, like this holding pattern shape doesn't self-intersect. Like if you were thinking about detecting self-intersections, that's a perfect example of where it doesn't work, but you still want to label this as a holding pattern. Also, it's not always really parallel, right? Here, like on this right-hand side, you can see like when they get out of the holding patterns, maybe they have to take the distance with previous aircraft, so they are, yeah, not so parallel on this side. There is nothing parallel here, but it's actually entering the holding pattern and not finishing it. You will still want to label it as a holding pattern. This, you see, like it's also a weird shape, and you can guess that it's also entering and exiting the holding pattern without actually doing it. Here you see also some weird shapes that has been labeled by the model in the end. And also, like when you see a lot of self-intersection going in, going back, that's an example flight in the documentation of the library. Actually, you don't want to detect holes or loops, you just want the holding pattern, and it matches it pretty well. So, what's the problem? Like when we do machine learning, we need a labeled data set. So give me the labeled data set. You have it? No, we didn't have it either. So actually, we don't want a yes/no answer. We want a bit more than that. Like we have the trajectories. We don't want to say, is it a holding pattern or not? We want to know exactly when in a trajectory we have the holding pattern. So it's not really a classification problem. It's also a detection problem, like identifying in a picture where is the cat, right? We don't want, is it a cat or not? Like we want to know where it is. We know, the thing is, yeah, in our previous contribution, we did quite some stuff about deep clustering. The idea with deep clustering is that you have already some machine learning model, usually based on autoencoders. So an autoencoder is a model where you have an input, and the expected output is your input. Yeah, useful, right? Why it's interesting is that it goes through layers with a much lower dimension. And so actually it's nice to have those models because you get a representation of your input data in a much smaller space where it's easier to define a distance. The idea in the end is that when you build this kind of models, trajectories that look alike, that are close to each other, they would be neighbors as well. They would be close to each other in the latent space. Since it's hard it's very hard to define a distance between trajectories. Like it doesn't work very well in big dimensions. So if you project your data to a smaller dimension, then the Euclidean distance starts to make sense, and you can work there. So we have actually, when we built a model, we had 2 steps. So first we labeled the data set, and then we trained the model. So the thing is, like, we had so many trajectories, we don't want to label them all manually. So we did some unsupervised learning first to try to understand how the data structures in this latent space. Do a first pre-labeling of the trajectory and then fix it before we can run an actual classifier then to say, okay, now we got the method that's currently working in the library. So first thing, label the data set. So the way we did for implementing this detection is that we first proceed with sliding windows. So we get a first piece of trajectory. So the way it's coded here, it says like we want segments of 6 minutes, and once we get it, the next one starts 2 minutes later, and we get 6 minutes. The next one's 2 minutes later for 6 minutes, etc. until the end. So we split basically all those trajectories in 6 minute segments. So why 6 minutes and not 5 and not separated by 3 minutes? It's just it yielded the best performance on what comes next. So just for the labeling part, just for helping to label, this was leading the best clustering basically in the latent space. So you see actually here, like it's in the end, the model we have, it didn't label this part. It's a machine learning model, right? It's not the Holy Grail. It's not the Holy Gospel. It's just some result. Here it labels only the second part. So we trained this autoencoder. So basically we have those 6 minutes, we resampled the trajectory into 30 data points. Then we do a very basic autoencoder. So we go through a layer with 8 neurons and 2, then back to 8, then back to 30. So that creates a latent space in the middle of dimension 2. So we can, every piece of trajectory, you can plot them, and we get this. And just actually we had some ideas of some pre-labeling, very manual, very quickly to get, where are the holding pattern in the latent space? And you see actually, well, there are some go-arounds, there are some many other things, and it clusters somewhere in the middle, and you see, oh, actually, we have holding pattern here. A bit here also too, but maybe we want to cluster this part so that we can pre-label our data set and say, okay, these are the holding patterns and these are the not holding patterns. So if you take, for example, this trajectory, basically, just so that it's clear for everybody, when we have a long trajectory, you draw a path in this latent space. Like in the beginning, you don't have a holding pattern, then you have a holding pattern, blah, 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 blah. And then you get out of the holding pattern because you just go landing and you're back to the area in the latent space where it's not a holding, it's just a regular path. So we need to cluster first this latent space. So in the end, just some basic Gaussian mixture. We just know where the holding patterns are basically. Manually, we found, okay, with a Gaussian mixture, we have this orange cluster that matches roughly where we have holding patterns. And we run a pre-labeling on our whole set of trajectories for all those flights, and we will adjust it. So we marked all the segments as a holding pattern, and as I said, like quality was average. Like I say, imagine the Google Translate level when you have ChatGPT, right? So not that good, but it's still a good first start that you can fix, and you spend less time labeling than if you start doing everything manually. So we built a very shitty tool. I would say we had 2 plots. You click on things, and like on one side of the plot is like the holding patterns. On the right side, the not holding pattern. We take batches of trajectory. We click on it. Like if it's not on the right side, you click, it goes on the other side. And when you finish your batch, you go to the next batch. and you store the results, and it's not fun. So you could say, yeah, ask ChatGPT, right, to do the labeling for me because it answers all the solutions. Actually, it works very well at describing the feeling it is to do this labeling. So yeah, that was 100,000 flights roughly. So about 800,000 segments that we labeled, and you see the balance is only 500,000 of those segments were positive holding patterns. Then we train a classifier. So that's actually, well, you have the data set, so you just train it, you get your performance. That's so just to remind, we get the sliding windows. We worked only with a track angle. That's when I say unwrapped, is that you don't want those gaps between 359 and 1 degree. You want to keep going to avoid this discontinuity. So we unwrap it. We do some min-max scaling. And then we have this convolutional architecture that we built. Well, this is, okay, just facts, like that worked. With trains to split and train and test. In the end, what we didn't want to do is over specialize on one airport, just in case. So we tried learning on 3 airports and test on the other one. In the end, the best result we had by keeping Dublin as in a testing set, and so using the other airports for training the data set. So yeah, about I don't keep accuracy here in the metrics because since the data set is heavily imbalanced, the accuracy doesn't mean much. But we get, yeah, for precision, but 85%. It doesn't look perfect. There's something also we need to remember, since we're working with those sliding windows. It's pretty tolerant to mislabeling, because if you have, let's say, a segment in the middle of your trajectory that's wrongly labeled, actually it will be fixed by the other overlapping segment saying it's a holding pattern. So it's in the end, that's why it works pretty. That's one of the reasons why it works pretty well. Yeah, just a word also about using this intersection over union. So that's a usual metrics for detection machine learning models. What you want when you do detection is basically, okay, you want to find where the truck is. So you don't want a big box, you don't want a small box. That's the intersection over union is a good union to have the right size of the box, marking where the truck is. So we did the same thing with a holding pattern, try to find, does it work well at selecting the right amount of holding pattern. The thing is also, we were several people trying to do the labeling job, fixing the labeling job, and we don't always agree, even with ourselves, when we do the labeling, where does it exactly start in all those corner cases. So that's also one of the reasons why the intersection of a union doesn't look very good, but in the end, the method works quite well. And especially if you just need to select, give me all the trajectories where there is a holding pattern, the intersection union over a union doesn't matter very much. So that's all. Some takeaways. When you don't have a labeled data set, this unsupervised learning can help to bootstrap a first labeling that you can fix later. So now we have a labeled data set that is public. Actually, the whole labels, they're ready to be public. I realized I forgot to share them online, but it will be done. Cost, yeah. And we have the models, in NX format, so usable in any other programming language. If you want to implement them in Fortran, for example, be my guest. And that's how then we can write this kind of code now. So actually, the next plot is a bit more than that, but how does it work? You just take this data set that we have, so all those trajectories landing at London, say, give me only the one who have a holding pattern, and give me 600 of them. You plot them first in gray, and only the holding pattern part, you color it in orange, and that's what you get. And happy to take questions.
Thank you, Xavier. Bunch of questions. Go one by one.
Most of the holding patterns usually are published on charts, but did you use that as a ground truth in the first step, maybe to like?
No.
Okay.
The thing is, I didn't want to, use those published data points because you also have holding patterns that are not on holding patterns, especially in emergency situations. Yeah. So it's like, some people would say, if you want to detect the holding pattern, you say, are you going several times through these labeled data points? But actually there are also corner cases where you miss a lot of them.
Just for a portion, maybe as a starting point,
Yeah. Well, I didn't do now.
Okay.
I'll go there first, sorry.
I had the same question.
Okay.
Thank you for the presentation. I was just curious. So about like go around and holding patterns, like how to differentiate like these two like pattern that has like some similar patterns, go around and holdings.
Ask the machine learning model how it did. I mean, I just labeled it. I didn't. The thing is, at first also we introduced, in addition to track angle, try to introduce the vertical rate, thinking like maybe it would help differentiating these things, but actually we don't need it. It just works.
So I have a question in the same direction of the first one. If you don't use it for labeling, but maybe providing it as a feature to the network, like the waypoints of the airport, like the distance to the holding pattern waypoints.
The thing, as I said, is like you have also a lot of holding patterns that are not near airports, especially in emergency situations. They do some holding patterns anywhere for running the checklist, and you want to detect them as well without any. They can happen at very high altitude just because they need to run the checklist.
Of course, but you could still improve the accuracy by having them because most of them will take place in.
Maybe that would have been helpful to label the data set more precisely, but the first clustering thing did a good like. The thing is,
I will use your code and I'll test it out and I'll come back to you.
Sure. And you can submit a pull request if you fix it.
Yeah, as an American, I'd be concerned about that because we see holding patterns like hundreds of miles away en route going into New York. So I'm glad you didn't use airports as a feature. I'm more interested in the labelers at this point.
Okay.
Who labeled, what was their proficiency, and is the label like...
The authors labeled.
The who did?
The authors of the paper, of the non-existing paper labeled.
I didn't catch all, but we can certainly imagine there's varying levels of proficiency and understanding of aviation. And so...
I mean,
so my question is, if
we agree with each other, basically.
Right, yeah, and you might not even agree with yourself. So does the data set include who labeled what?
We can add it. Because we did, basically we shared by airport, so.
Okay. Yeah, I'd be very interested to see that. Right, and especially.
I don't know why I picked London Heathrow. I hate myself.
Yeah, and the other question is, do you have the timestamps of when the labeling was made? Is that in your data set?
And it's not, but we did like, just like 1 hour a day, just like at the end of the day, I don't want to work anymore. I'm going to do some frenzy.
So the reason why I'm asking is we do similar tasks. I do Homeland Security natural language processing work. And we are very careful about labeling, getting our annotators who annotated what. So we have inter-rater agreement, but also when did they do it? At the beginning of when they started this task, or at the end, because we see maturation and the learning.
Yeah, you're
in their
learning as well.
process.
That's true.
And so
we did only one pass.
Yeah.
And
so that in itself is, I think, within the idea of open data, it's understanding.
Yeah, and we did
as
them in order,
researchers,
but we tell, all those segments are numbered. We did them in order.
Okay.
And
Oh, good. Yeah. So I'm very excited to look at the data set.
Okay.
Thank you.
Next question.
Thank you. Congratulations for those excellent results that are very impressive. I have a question regarding a potential improvement of the detection algorithm. As you pointed out at the beginning, there are several ways of altering the holding pattern. You could make a direct entry, a teardrop entry, a parallel entry, and so on. And the selection of the entry is very well codified and depend on the angle of the initial approach and the holding pattern.
Sure.
Is it have you taken into account those, let's say, regulated entries in order to improve the accuracy of the holding pattern detection?
So the model maybe does it, maybe not.
Yeah, indeed, as it is machine learning, it may do it. Yeah, you are right. Thank you.
Okay, and we'll take one more question online, and then we'll have to move on. Can you read it, please?
Sure.
So there's one question from Gerard. How does sampling rate of the trajectory affect the classification performance? If the data is of different sampling rate than your data set, would a retraining be necessary?
So what the model, when the implementation does, is to take those 6 minutes, and they basically downsample them usually to those 30 points. That is 30 points for 6 minutes, that make 5 points per minute. So like one sample every 20 seconds. No, every 12 seconds. So yeah, otherwise it would, if it's not enough, it would upsample it. But like the resampling part is done. I just think it's more reasonable to have to downsample it. So if you have, let's say, if you have at least, I'm just reasoning out loud, right? But like if you have at least 1 point every 10 seconds, let's say, that should be enough for detecting for the model to work. And there's another comment now?
Yeah, one more.
Oh, it's okay. We can, we can discuss on the Discord later as well, if you want.